All right, hello. So I'm going to talk over these adapted slides here again from a later edition of our textbook for sections 7-3 and 7-4 about estimating a population mean. These slides will kind of combine ideas from both of those sections. We're going to start actually with ideas from section 7-4. So this section presents methods for using the sample mean to make an inference about the value of the corresponding population mean. Basically meaning we're going to use confidence intervals to estimate population means. So keep in mind for the previous section, we estimated population proportions using this formula for confidence intervals with proportions, or we had p hat plus or minus the z critical score, then times the square root of p hat times q hat all divided by n. So that format of having some sort of sample statistic plus or minus a critical value times a standard error, that's still the same for when we use confidence intervals to estimate a population mean. And now the difference is that with the population mean confidence intervals, we're starting with that sample mean plus or minus some critical value times the standard error. Now, we have two different confidence interval formulas for population means. Notice one has a z critical score, and there's a new variable here that has a t instead. And key differences are that one of these we'll use when we know the population mean, and the other one is what we'll use when we only know the sample mean, so we don't know the population mean. And I'm going to start actually with ideas that use this confidence interval here, because that one is actually the more important of the two, since realistically you won't always know what the population standard deviation is. So again, when you only have the sample standard deviation, that's more important. So key concepts here, again, we should know the sample mean x bar is the best point estimate of the population mean mu. So that should be more review still, hopefully. And we should learn how to use sample data to construct a confidence interval for estimating the value of a population mean. And we should know how to interpret such confidence intervals. Again, interpretations are the most important parts of confidence intervals. And we should develop the ability to determine the sample size necessary to estimate a population mean. So very similar concepts to the previous section, just now using confidence intervals for population means. And just about all the same conceptual ideas will still apply. So some requirements for when we start doing confidence intervals to estimate a population mean is that in these cases we want the population to be normally distributed, have the sample size be greater than 30. And we want to make sure that we're dealing with simple random samples each time. All right, now we're going to be using a different distribution for these first kinds of confidence intervals when we do not know the population standard deviation. So we're going to use what's called the student t distribution. So how this is characterized is if the distribution of a population is essentially normal, so just about normal, then the distribution of this whole nonsense here, t equals x bar minus mu divided by all of the standard deviation over the square root of n. So it's essentially just divided by the standard error. You do not need to worry about this mess of a formula, at least in this chapter. Just know that this is essentially what we're using to find the t distribution, which is distribution we'll use instead of the z distribution for these confidence intervals. So this is called the student t distribution for all sample sizes of n, and sometimes it's shortened as the t distribution. And what we ultimately use this for is to find critical values denoted by t sub alpha over 2, is how they're denoted in this book. And you may also see this as t sub c, for example, just standing for the t critical value, similar to how we use z critical values in the last section, just as z sub c. Now, something that's important with this distribution is that we have to take into account the degrees of freedom for t distribution. For a collection of sample data is the number of values that can vary after certain restrictions have been imposed on all data values. This is kind of what the degrees of freedom means. Now it's often abbreviated as just df, and so in order to find the degrees of freedom, you just take the sample size and just subtract 1, and that's how you find the degrees of freedom for any sample set. This definition might sound a little bit strange, as saying the number of sample values that can vary after certain restrictions have been imposed. Say, for example, you want to find the mean of 4 test scores. Then you can you want the mean of 4 test scores to be a certain number. You can make the first 3 numbers anything you want. Then you'd have to make the 4th one something specific in order to get the mean that you want. That's kind of what it means by sample values can vary after certain restrictions. So you need just one of them to be a certain value. So that's why the degrees of freedom is n minus 1. All right, and so where we're going to see those t critical values, of course, is in the margin of error still for confidence intervals, since the margin of error is just equal to that critical value times the standard error, which in the case of when we don't know the population standard deviation, the standard error is just the sample standard deviation divided by the square root of the sample size. And again, where that t critical value has n minus 1 degrees of freedom. And there's another table in the back of your book that I'll also post to Canvas and here where you can use that to find your t critical values. I'll show you how to do that in just a little bit here. Now just to clarify again the notation, so mu still stands for our population mean, x bar as our sample mean, s is what we'll use for the sample standard deviation, n being our number of sample values, e as the margin of error, then t sub alpha over 2, or we could use t sub c, essentially just standing for that t critical value. And similar to z critical values, the alpha over 2 stands for the area to the right of some value in a distribution, but it can be that same area on both the right and left ends tails of the distribution. So the confidence interval formula just, what the confidence interval will look like for when we find these ones that estimate population means. Again, is we can use this inequality notation, just finding what number we would get after doing x bar minus the margin of error, less than mu, then less than whatever number we get for x bar plus that margin of error, or we can use that parentheses notation. Both work. Or we just got to keep in mind that's what our new margin of error is, just t critical value times that standard error for population means, or sample means. So general procedure is just verifying that our requirements are satisfied. So again, just knowing that we're dealing with a simple random sample, and then we have a sample size greater than 30 or a population is normally distributed. And using that n minus 1 degrees of freedom, we'll use that table A-3 or the t table to find our critical value for whatever confidence level we're dealing with. Find our margin of error. Basically just kind of plug everything in to figure out the actual numbers for our confidence interval, and then round anything as needed and interpret the confidence intervals. So here's an example, and I'll show you what the t table looks like in just a bit here. So a common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol in milligrams per deciliter, I believe is what that means, have a mean of 0.4 and a standard deviation of 21. So use the sample statistics of n equals 49, x bar equals 0.4, and the standard deviation equals 21 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. Then we'll be answering after, what does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? So requirements were satisfied. We've got a sample size bigger than 30, and we're going to be dealing with a simple random sample. So this 95% implies that essentially the leftover percentage is just 5% there. And with n equals 49, then that means our degrees of freedom is 48. Now, when we actually take a look at the t-table, so this is what the t-table looks like, and you can look in whichever column you need, depending on if you're looking at the area in one tail or the area in two tails. For confidence intervals, we're always going to look in this area in two tails, because essentially when we're finding our confidence interval, again, we're looking for that middle percentage is where we're saying that our confidence interval will end up at. So like if it's a 95% confidence interval, for example, we have that middle 95%, and then these two tails make up the remaining 5%, which is what that alpha level is. So alpha over 2 would be 2.5% here, 2.5% here. So since we have the area in two tails is what we're looking at for this one, then we'll have that leftover alpha again of 0.05. Now, looking in this t-table, these are all my degrees of freedom values over here, so all my n-1 values. So if I had a sample size of 2, then this would be where I'd look for my degrees of freedom of 1 and look for the respective critical value. But notice I don't have every possible value that I want. So like for this particular problem, I don't have a degrees of freedom of 48 anywhere in here. The closest I have is 50. So then I'm going to look in this row for 50. And I got to make sure that I'm looking again, area in two tails in for 0.05. Look in the 50, and then I find that critical value of 2.009. So then that tells me that's what I'm using as my critical value. It's just the 2.009. So that's where that's coming from here. So now using 2.009 for the critical value, then standard deviation as 21. See, we just know the sample size there. Then we plug all that in to figure out what our margin of error is. So that critical value, 2.009, standard deviation, 21, should be an S there just for sample standard deviation. Then our sample size, 49. And again, once we just plug all that in, we get 6.027 for that margin of error. Now we just construct that confidence interval with x bar being 0.04, and margin of error is 6.027. So plugging all that in, we get 0.4 minus 6.027. That comes out to negative 5.6. Then 0.4 plus 6.027 comes out to 6.4. So our confidence interval is between negative 5.6 and 6.4. Now when we interpret that, and this conceptual interpretation is very much the same as it was for proportions, just now it's for a mean instead. So we are 95% confident that the limits of negative 5.6 and 6.4 actually do contain the value of mu, the mean of the changes in LDL cholesterol for the population. Now, because the confidence interval limits contain the value of 0, it is very possible that the mean of the changes in LDL cholesterol is equal to 0, suggesting that the garlic treatment did not affect the LDL cholesterol levels. So we can say conceptually for this one, it does not appear that the garlic treatment is effective in lowering LDL cholesterol. So there we go. We just did an example of finding a confidence interval to estimate a population mean. All just using that new t-table for critical values and that new formula. Now I'm going to pick up in the next video with some of these important properties of the student t-distribution and go from there.